Our second competitor is David Gozzard from the Frequency and Quantum Metrology Group in the School of Physics. David is in the second year of his PhD under the supervision of Winthrop Professor Michael Tober and Dr. Sasha Sradaway. He enjoys teaching first-year astronomy and astrophysics and has been heavily involved in surf life-saving for the past 11 years. His thesis title is Stabilised Transfer of Time and Frequency for Space Science Applications. His 3MT talk title is A Matter of Time, Stabilising Signals for Precision Space Science.
Time is a funny thing. It flies or seems to stand still. We try to save it or kill it, and most of us can't seem to find enough of it. But why does time matter so much? We know time is important, but for most of us, in our daily lives, clocks much more precise than a second are pretty pointless. To be here together, we only had to agree on a day, an hour, and some minutes. And the timekeeper needs seconds to make sure I don't talk too long. The only time we need something more precise is when Usain Bolt shaves another few hundredths of a second off his previous world record. But physicists, like me, want to measure time even more precisely. We do this because accurate and precise timing is not just an important part of scientific experiments, but because it is the cornerstone of our technology and civilization. Today, most of you will have used the internet. To get here, you might have used GPS. Almost certainly you have used your mobile phone. We take these technologies for granted, but all of these technologies depend on timing far more precise than seconds. They depend on atomic clocks, which are capable of measuring time to less than a billionth of a second. These atomic clocks must be synchronized worldwide and out to hundreds of satellites in space. If our digital communication systems can't synchronize precisely, transmitted data will simply be lost, and so will we. As atomic clocks get more precise, we stand to reap huge benefits from more precise navigation, better communications, and science experiments that will help us to unlock the laws of the universe. But there's a problem. The full precision of the latest atomic clocks cannot be transmitted using current techniques, such as radio waves. The clocks know exactly what time it is, but they can't tell anyone else. We need better ways of sending ultra-precise time signals over vast distances. Transmissions using lasers over fibre optic cables are promising, but they are very sensitive to disturbances such as vibrations from vehicles and daily temperature variations that stretch or shrink the fibre optic cable and degrade the signal. I work on ways to stabilise the atomic clock signals by developing systems to measure these disturbances and compensate for them. By bouncing part of the transmitted signal back from the receiver and comparing it to what the signal should have been, electronics can adjust the transmission accordingly. Stabilised time transmission is already being used in science experiments. I'm involved in two major projects. One synchronising radio telescopes with a square kilometre array, and two transmitting atomic clock signals to the International Space Station. Soon we will find the benefits of more precise time right here in our own pockets. It's only a matter of time.